First and foremost, I would like to thank the organizing committee of the World Renewable Energy Council for giving us the opportunity to present our work titled Advancements in High-Performance Hybrid Photovoltaic Thermal Solar Collector Technology. I would like to also thank the chair of the session, Dr. Salam Darwish. My name is Al-Waeli, and I will be presenting this research on behalf of myself and my colleagues and co-authors, Dr. Qamar Zaman Sufyan and Dr. Hussein Kazem. The aim of our research is to present an overview of the latest research on the design and development of photovoltaic thermal collectors. I will be referring to photovoltaic thermal collectors as PVT. The protocol of our research is a standard review paper. I will give a brief introduction on the topic. We'll move on to PVT collectors, and then we'll discuss the advanced PVT collector. On the right side of the slide, you will see a solar cell or a PV photovoltaic cell. And as you know, a photovoltaic cell is a semiconductor device that converts sunlight into electricity. Commercially, you will find it as a photovoltaic module, as you can see on the left side, which is a single unit that contains a number of solar cells within a frame and a glass cover, backing material, and a polymer sheet. Now, the solar cell is affected by solar irradiance, ambient temperature, wind speed, humidity, shading, many parameters affected. The cell temperature is a parameter where if the cell temperature increases, then the electricity generation or the electrical yield of the solar cell will drop down. This is because a decrease in the open circuit voltage can be observed when the temperature of the solar cell increases. However, a slight increase in the short circuit current can also be seen when the temperature of the solar cell increases. Overall, the power will drop down and the efficiency will decrease as the cell temperature increases. Therefore, there needs to be a solution to mitigate this problem. How can we cool down photovoltaic modules when they are being used? Another technology in the solar energy sector is the solar thermal collector, or is known as the solar water heater, where you can see a number of tubes within a collector that will have fluid running inside, and the working fluid will gain the heat from the sun. Therefore, you will produce thermal energy. Conventionally, you will either see a photovoltaic module on a rooftop, for instance for residential purposes on a house, or a solar thermal collector. You can see both of them depending on the user's requirements, but you can rarely see a PVT collector, which is a photovoltaic thermal collector. What is it? It's the emergence, or is the combination of the two together. As you see in this slide, and in the center of the slide, the cooling tubes or cooling pipes are attached to the back of the PV module. A fluid will be pumped within these pipes, within these tubes, and therefore it will cool down the PV module and produce thermal energy at the same time. There are many classifications of PVT collectors. It could be classified based on the fluid that runs within the collector. For instance, air-based PVT. Here you can have a single pass, like a channel, a double pass. So you could have a channel or two channels that allows the air to flow in two directions. You can have a water-based system, a water-based PVT. You can have a combination of both. Concentrated PVTs have a concentrator combined with the system, such as the CPC compound parabolic concentrator or the Fresnel lens. There are advanced designs that we have found in the literature, such as the heat pipe-based PVT and the nanofluid-based PVT system, and along many others. So, our research question is simple. What are the latest advances in PVT system design? How does this affect the industry? How does the latest research advance the state of knowledge? Well, some of these advanced designs that we were able to provide here in this presentation include PVT with fins and CPC. Here you can see there's a PVT with a single flow and a PVT with a double flow where the air will go through two directions. This is just for a PVT with fins. If we add a CPC, a compound parabolic concentrator, then we can maximize the amount of solar irradiance on the surface of the cell, and at the same time we can dissipate the heat using the fins. This is a simple design, however it can be very effective. Here you can see a prototype and its installation in real time in Malaysia. Another type of systems is the photovoltaic thermal with nanofluids and phase change material, but we can have them separately. So what are nanofluids? Nanofluids are fluids that contain nanometer sized particles. These particles are mixed with a base fluid that improve the thermal conductivity of this base fluid, for example. Therefore, they can be very beneficial for heat transfer applications. They have been used for solar thermal collectors, and in the last 6 years they have been used for PVT systems. Here you can see one of the known methods of preparing nanofluids, which is called the two-step method, where nanoparticles are obtained in powder form and then they are mixed with a base fluid such as water in an ultrasonic bath or a ultrasonication probe, and then they can be tested for their thermophysical properties, viscosity, density, thermal conductivity, maybe specific heat capacity as well. And here is an example of how nanofluid could improve the power of the PVT system. You can see at 1000 watt per meter square of solar irradiance, a PVT with water running within will produce 80.6 watts. A PVT with a nanofluid will produce 93.4 watts. You can see there's a difference in power production, higher power production that is achieved when employing nanofluids. This is another example of a grid-connected PVT system compared to a grid-connected PV system, where you can observe on the left side a decrease in the temperature, more decrease in the temperature, or a lower temperature for the system that uses nanofluids, which means, as you can see on the right side, it will produce more power. This is a PVT with nanofluids and nanophase change material. As you can see in the layers, the top layer is a PV, and then you will have a layer of nano PCM layer. PCM refers to phase change material. An example of phase change material that is known is a paraffin wax, an organic paraffin wax. Now, phase change material have latent heat properties. They have high latent heat, which means they can be excellent energy storage material. However, they have low thermal conductivity. Therefore, adding nanoparticles to phase change material can improve their thermal conductivity. In this application, the nano PCM is used to store the heat from the PV module. That's why it is poured at the back of the PV module. Now, this heat needs to be extracted. Therefore, you can see copper pipes being submerged within the nano PCM layer, and within these copper pipes, nanofluids will flow to collect the heat. This is an example of the prototype. And here are some of the other designs that we have found, state-of-the-art designs in PVT research, such as the use of thermoelectric generators and phase change materials. Here is an example of a photovoltaic module with an array of thermoelectric modules or thermoelectric generators. These thermoelectric generators utilize the difference between the hot side and the cold side of these modules to produce electricity. Therefore, we can increase the electricity production of the system without adding or without it being costly for more area, without utilizing more area. Here you can see an example of 19 thermoelectric generators being placed at the back of a PV module, flipped, or a PVT, at the back of a PVT module in between the copper pipes. And here is a design of a system that is both concentrated PVT and also utilizes phase change material, a heat sink, and a thermoelectric generator. Here's another example of the use of PCM and nanofluids, but with a thermoelectric generator. As you can see, the thermoelectric generator is placed around it. There is the phase change material, and then we have a copper pipe which will carry nanofluids. Now, with regards to PVT systems, there are also innovation in PVT systems that are building integrated. Here you can see an air-based PVT system that can be very beneficial for summer and winter time. During winter time, it provides heat to the building, and during summertime, it utilizes the exhaust air to provide thermal energy for other purposes. So, what are the conclusions and what is the future directions in this field? First of all, when we talk about how does the latest literature reflect on the industry, well, let's talk about what does the industry benefit from this, from a technical point of view and from an economic point of view. As you can see here, over the course of the years, different types of PV modules from different manufacturers will degrade in terms of performance. So their output degrades over time. This is due to the thermal stress. This is due to the usage of the PV module for long periods of times and it being exposed to the various elements of weather. So being able to mitigate the temperature issues can be helpful in increasing the electrical yield of the PV module and also in maintaining the lifespan of the PV module. Here you can see some of the economics where you can see the payback period of different types of advanced PVT modules compared to a conventional PV module, all of which are grid connected, which are installed in Malaysia under the feed-in tariff system or program. And you can see that the black arrow shows how the conventional grid connected PV will begin to give a return on the investment at the 15th year mark, while the other advanced designs, for instance a PVT using water or using nanofluids or using nanofluids and phase change material, you will have a shorter payback period. And so lots of the new research focuses on reducing the payback period and the cost of energy of the proposed systems or PVT designs. So what do we recommend? Well, we recommend creating an international environment that enables the industry to develop PVT systems. There seems to be a lack of knowledge on this topic. There also seems to be some discrepancy between the advanced research and the non-existent industry when we talk about PVT. Essentially non-existent. There have been companies that produce PVTs, but not to the level of photovoltaic or solar thermal. The other thing, which would be the medium term, so this is 3 to 5 years in the future, will be to try to work more on the cost of the PVT technology, try to drop down the cost, improve the aesthetics, makes it more user-friendly. And over the long term, so this is 5 years or more, we want this technology to arrive into being integrated PVT products or systems because they are techno-economically sound. Now, it is important to note that there are lots of advanced designs. However, there needs to be criteria to judge these designs. Among the criteria will be techno-economic evaluation of whatever is proposed, because we want to avoid over-engineering these collectors. Finally, I would refer you to our book, Photovoltaic Thermal PVT Systems, Principle Design and Applications, if you want a more comprehensive description of PVT systems and more knowledge on the topic. And finally, thank you all for listening and for your attention.